All right, hello everyone. I am Elizabeth Gonzalez. I am a second-year PhD student at Penn State University, where I'm working with Suphrav Mahadevan on trying to explore granulation mitigations in the context of radial velocity detections. So bear with me, as the next couple of slides will be a little bit repetitive, but for the sake of completion, I'll still kind of go through them a little quickly. So I officially have had this slide covered for me. So the radial velocity method has detected hundreds of exoplanets since its first detection in 1995. And here I'm showing said exoplanets. And as you can see, the radial velocity method has hit a floor around 1 meters per second. This is not because of our instruments. Our instruments have pushed past this boundary. For example, the Newt spectrograph, which I will be discussing and using for my observations in this project, has an RV precision of approximately 27.5 centimeters per second. What is causing this floor, as we just so nicely heard in the last presentation, this is due to stellar variability. Now, stellar variability can manifest itself in a variety of different ways, as we've heard of thus far. Most of these variabilities do have a mitigation method associated with them to mitigate for them. The exception here being granulation, supergranulation, as we have so keenly heard thus far. For granulation specifically, this introduces radial velocity shifts and signals from 0.1 to 1 meters per second. So if you want to get towards the precision needed to get an Earth-like signal around here, which is a RV signal of 9 centimeters per second, we really need to find a way to model and accurately reduce and remove the granulation signals. So what is granulation? This term has been coming up so far a lot in the day, so I figured I'd just do a kind of breakdown of what it is and be more in depth. So I'm showing you this movie here, which we've seen at least I think in 3 talks now, and ultimately you have the 2 components of the granulations, your granules and your intergranule lanes. So your granules are going to be depicted in your brighter yellow regions. These are comprised of your hot upwelling plasma. As this plasma rises, it's going to cool and it's going to fall back down into the star, creating the intergranule lanes, which are depicted in the brown regions surrounding the granules. These are going to be overall cooler, denser, and like I mentioned, downwelling. Luckily for us, we do have a really good understanding of how granulation impacts our line profiles. So I'll go ahead and do a quick review of this, given that Michael Palumbo discussed it in his talk as well. But ultimately here on the top left corner, you have the 2 components of granulation, and in the bottom left corner, you have them co-added to 0 approximation. In this net profile, we have the granulation signatures that manifest themselves. First one being this overall broadening, our line's getting narrower, it's getting wider, boring. More interestingly, though, is that we have this asymmetric in our net profile, and this is due to the fact that we're receiving an unequal amount of photons between lanes and the granules, with the lanes producing less photons. And as a result of that, our wings, specifically our red portion of the wing ring, is going to get damped because of the unequal amount of photons, producing that asymmetric bisector. In addition to this, we're also going to get a net convective blue shift in our lines, and this is due to the fact that our granules are so much brighter and are so much larger in size. Therefore, they're going to dominate the wavelength shift in the net profile, causing a net convective blue shift. Now, in addition to all of these signatures, we actually also understand that these signatures are going to vary depending where you are on a stellar surface. So to determine where we are on the stellar surface, I'm going to be using the variable that we've seen so far, mu, and this is the cosine of our solar limb angle. So mu of 1 means that we are at star center, and as mu goes out to 0, we're going to go out towards our limbs. And here on the right, what I'm showing you is that for a given line, in this case, the iron 5434 line, I'm showing you how the bisector is going to vary depending where we are on the solar surface. So mu of 1, sun surface, we have more of a C shape in that bisector, and as we go out towards the limb, it becomes more of a backslash. So we now understand what granulation is. We also understand the effects of it, how are we going to mitigate for it? So in my project, I'm actually using the package and software that we heard from earlier, GRASS, our Granulation and Spectra Simulator. Just a really quick overview. This is ultimately going to create synthetic spectra that has granulation-driven variability. Let's really quickly go through the process of how this is done. So GRASS is using input data from the LARS spectrograph in the Canary Islands that has observed 22 lines at each one of these blue ticks in the image on the left. So we have a center to limb knowledge of how these lines are going to vary across the surface. We measure a line bisector and a width for each of these lines, and then a user can go in and create a simulation of a spatially resolved disk surface. We can do a spatial integration of the surface, and from there we can get a disk integrated synthetic spectra that has granulation-driven variability. So that's the model I'll be using, that's the tool I'll be using to create my models. Let's talk about the data. So since I started my PhD, I've been so lucky to have 2 solar eclipses occurred in the US. I'm providing you here the paths and the relevant information in the table. Unfortunately, the April one was kind of cloudy, so we're going to just ignore that for the sake of this talk and for most of my analysis for the past 1.5 years. So I'm going to focus on the October one. All of this is being observed from NUID, which is depicted here in the green arrow. NUID is a highly stabilized spectrograph, has high resolution of 100,000, and it's in the optical range, and like I previously mentioned, has an RV precision of 27.5 centimeters per second. So what exactly is the role of solar eclipses? So in the theme of this section, the sun as a star observations, ultimately the sun is disk resolved, but we can use a solar telescope, of which here I'm showing you the solar telescope diagram for the NUID solar telescope. Our disk resolved light will go into it. It'll hit this integrating sphere where the light will scramble and will come out disintegrated. And this is what we'll be using for the solar eclipse observations. In addition to that, we also have an amplified Rosser-McLaughlin effect. And as we previously have mentioned, that the curve, for the shape of this curve is going to be highly impacted by convective blue shift. Here I'm showing you a previous study, Reiters et al. 2016, that analyzed the March 2015 eclipse. And here what you're seeing is their data in the black X's, and then 2 different models. The model on the left does not account for convective blue shift. We have higher residuals here, and our data is shifted towards the blue because it does have an influence from the granulation convective blue shift. And then on the right, we introduce convective blue shift, and immediately you see a reduction in our residuals. So all this to say that when we're trying to model our solar radial velocities, especially during a solar eclipse, it's crucial for us to account for convective blue shift being introduced by granulation. So here I'm just giving you a general pipeline of how I'm creating my models. Ultimately, I just grid the sun's surface. I use the NASA toolkit SPICE to determine all the appropriate orientations, determine which cells are being blocked by the sun. I consider some astrophysical concepts, which I will discuss in a second, pass this all into GRASS, simulate my line, and then I compute my radial velocities using a CCF to be consistent with NUID. I fit a Gaussian to the CCF, and the mean of that Gaussian will be my radial velocity. So here I'm showing you the NUID pipeline radial velocities. As I mentioned, this is using a CCF to determine the radial velocities, but it's doing a CCF on a large array of lines. And in this project, I'm really interested in line-by-line variability, given that different lines are going to behave differently to granulation, some being more or less sensitive to the impacts of granulation. So what I've done is I've taken the NUID spectra, and for each of the 22 GRASS lines, I've extracted those lines and performed an individual CCF on those lines. For the rest of this talk, I'm going to specifically looking at the iron 15379 line, and here you see the individual line RVs. So moving forward, we'll look at these RVs. Now, before I run GRASS, there's a couple things I want to consider, and for this talk, I mostly just want to talk about my intensity model. Let's begin with limb darkening. So this paper came out last year that ultimately rightly pointed out that our limb darkening models have not been able to reproduce our observations, so our transit light curves from JWST, for example. Ultimately, our limb darkening models up until this point are using quiet sun observations. And all of this to say is that they're ignoring magnetic fields. And what this paper has found using MHD simulations is that by including magnetic fields, we can make up for this discrepancy. They modeled a variety of different magnetic field strengths, and they found that the best one to be using for the sun in this current solar cycle, and also in agreement, this is the best one I found, was their SSD, their small scale dynamo limb darkening model, meaning that we just have a minimum uniform magnetic field strength across the surface of the sun. So here what you're seeing is our transit light curve using the SSD limb darkening in the dashed lines, and then in the solid line, you actually have the true transit light curve observed from NUID. Large discrepancy here. Could we include extinction to make up for this discrepancy? So the extinction coefficient is rather unknown, given that it is a function of weather, for example. So all I've done is a chi-square minimization to determine my extinction coefficient, and I fed it into the Lambert extinction formulism, and in doing so, I can get a nicer match to the true transit light curve. So now we're ready to run GRASS. Here you have the initial results of our grass, which you have an RMS of around 17 meters per second, and our highest point in the residuals is around 50 meters per second, which is an agreement with the Reiners et al. 2016 paper. All of this to say that Reiner is doing a pretty decent job at modeling for the convective blue shifted granulation. Can this be pushed down further? The next thing I wanted to consider was P modes. Up until now, the community agrees that P modes can get averaged out if we're binning at around 5.5 minutes, given the P modes lifetimes. So I've done exactly that. And as you can see, we have a significant drop in RMS, which is great. P modes are at play. But I do want to question this, because is it still appropriate to be bidding for P modes at 5.5 minutes during a solar eclipse when we have partial blocking of the sun and we cannot average out our blue shifted and our red shifted hemispheres? This is something that's currently under investigation, and I hope in this project to quantify how we should appropriately be bidding for P modes. In addition to this, another thing I wanted to consider is that the input data for grass has a spectral resolution of 750,000. NUID has a spectral resolution of around 100,000. So we more appropriately should be convolving down this spectral resolution. And up until this point, I've been doing that with a Gaussian, which is not an appropriate representation of the NUID line spread function. The NUID line spread function is more of a mixture between a top hat and a Gaussian. So I've updated that convolution, and in doing so, we get a further drop in our residuals. And this is just a more direct comparison between the data and the model. This is all fantastic. In our residuals, we got a reduction around 3 meters per second. Remember, these are root mean square values, so we can subtract in quadrature. So we're truly actually modeling out 9 to 10 meters per second, which is fantastic. However, the photon limit for this line is around 1 meters per second. So what gives? Are we missing astrophysics? Should we be using limb darkening simulations for a given line rather than a continuum? Is supergranulation at play? These are all questions that I'm still currently investigating, and I would love to discuss with you if anyone has any ideas. But for now, I'll just leave my immediate future works on the screen and my main takeaways and take any questions. Thank you.
All right, thank you, Elizabeth. Questions for Elizabeth? It's getting late in the day. We can do it. There's only one more talk after this. All right, down here.
Hi, Tim Benning, Sydney. Thank you, very, very nice. How rapid is your sampling? What is your cadence of these spectra? Is it fast enough to sample the 5-minute oscillations?
This is a great question. So the NUID exposures are around 55 seconds. Currently, GRASS is using the input data that has a cadence of 15 seconds. So I'm actually currently investigating how exactly we should be doing the GRASS simulation to accurately match the NUID data. So ultimately, GRASS is appropriately and at the 15 seconds able to model and capture the effects of granulation, but now it's a factor of me and rewriting GRASS to be working for it to work in a solar system for the sun specifically, because that's not what GRASS is used for. How can I update it so then we have that accurate exposure to match the NUID data?
Right, but if you're observing every minute, you can see the P modes. You don't need to bin them, you can follow them. So,
Correct,
yeah.
yes.
So I wouldn't bin it. I would actually look at the power spectrum and identify the P modes.
Correct, yes.
Yeah.
Okay, I thought you were referring to the granulation. Yes, for the P modes, absolutely, I agree.
Great, thank you.
Hi, it's JJ Hermes from Boston University. The eclipse that you're observing wasn't total, right? It was only 70% or some percent. Can you help me understand the shape of the RM curve for something like that? Yeah, so ultimately, this is a flipped RM curve that you would expect for, like, for example, a star, and this is because of the barocentric motions within the eclipse. So here in the first half of this, as it drops down towards the blue shifted side of this, it means that our moon is transiting over the red shifted part of the hemisphere. So as the sun is rotating, we have those two different hemispheres, and in the case of the solar system, which is not what we would see for an exoplanet transiting another star, we have that reversal due to the fact that we're in the solar system, and then the moon is going to be transiting the red shifted half first. Yeah. I did have a movie, but I didn't include it because I started to question myself this week creating that movie that the tilt of my sun was incorrect, so I did not include the movie.
All right, time for one more question?
So you were wondering about the impact of having, a large fraction of the visible surface blocked and what that would do to the oscillations. I think that will make you sensitive to oscillations that you wouldn't ordinarily be able to detect if you were observing the entire disk. So modes that have higher spherical harmonics, basically. So you might be able to see that effect.
Yes, for the P modes, correct? Yeah. Yeah, I have no idea. Actually, Sufrev recently put a textbook that you wrote in my hands and was like, read this and learn about P modes.